So, good morning, good afternoon, good evening. This is the third talk in the series, The Universe Half an Hour at a Time. In the first talk, I described how, in 3 minutes, all of the hydrogen in the universe was made. In the second talk, The ABC of Stars and Galaxies, I described how all of that hydrogen made the stars and made the galaxies. In this talk, I'm going to be talking about black holes, which got a mention in the second talk, but only in brief. So I'm going to be describing a very brief history, an explanation of why light can't escape from a black hole. I'll be paying lip service to Einstein's theory of general relativity. Promise, no maths. And then I'll be asking the question, well, if black holes are black, how can we possibly see them? And I'll finish with, if the universe is full of dark matter, is that simply a large number of black holes? So, a brief history. Let's just make sure we understand the definition first. A black hole is a region of space from which nothing, not even light, can escape. And if we ask, when did the concept of a black hole originate, not necessarily the name, but the concept, well, that's probably a little earlier than you think. We have to go back to the Reverend John Mitchell, 1783, where he described the hypothesis that if we have a very large star, perhaps it would be so massive that the gravity would be so strong that light would not be able to escape from the star. So this idea of dark stars was pretty much ignored for all of the 1800s, and it only came back into vogue again in the 1900s. And there we had a number of individuals, starting with Einstein in 1915, developing his general relativity, and there were contributions from various other people. I'm not going to have time to talk about them, but their names and rough dates are there, so that if you wish, you can go and look them up and find out what their contributions were to our understanding of black holes. But one thing we do need to get right is the idea of what we mean by an escape velocity. So let's imagine we have an object. It doesn't matter what the object is. I'm standing on the surface of the Earth and I want to throw this object away such that it escapes from the Earth's gravity. How fast do I have to throw it? Let's ignore the Earth's atmosphere. It doesn't actually matter what the mass of the object is. Rather counterintuitively, it doesn't actually matter which way I throw it, as long as it's not down. I could throw it up, I could throw it at 45 degrees, I could even throw it horizontally. The speed at which I have to throw the object to escape the Earth's gravity is the same regardless. But the speed does depend on what I'm standing on. In other words, the escape velocity from a surface of a given body with a given mass depends on the mass of the body and the radius. Let's assume that it's a sphere. In other words, it's the distance from me standing on the surface to the centre of the mass that I'm standing on. And it's only that ratio of mass to radius that determines escape velocity. So we can put some numbers in and ask, well, if we want to escape from the surface of the moon, we put in the moon's mass and the moon's radius, and we find that we would have to throw an object at a speed of 2 kilometers per second. Or about 5,000 miles an hour. If we think about the Earth, it's a bigger radius, but it's a much bigger mass than the moon, some 100 times larger, and so the escape velocity is higher. To escape from the surface of the Earth, we would have to throw an object at about 11 kilometers a second, or about 25,000 miles an hour. So when the Apollo astronauts were sent on their journey to the moon, the Saturn V rocket had to get them up to a speed of about 25,000 miles an hour so that they could escape the Earth's gravity and go coasting their way to the moon. If we imagine for a larger body, for instance the surface of the Sun, not advisable, but if you were standing on the surface of the Sun, again a larger radius but a much bigger mass, then the escape velocity from the surface of the Sun would be 600 kilometers per second, or more than 1 million miles an hour. And that sounds ludicrously fast, but remember that even that speed is only a fraction of the speed of light. So we're not even close to a position yet of making a black hole. So let's do a thought experiment. Let's take the mass of the Sun and compress it into a smaller volume. So we're not changing the mass, but we are effectively changing the radius of the sphere that we're packing all of that mass into. As the Sun gets smaller, the escape velocity will go up, because remember, the escape velocity depends on mass divided by radius. And we can plot that on a graph here, where we're going to plot the escape velocity on the vertical axis as a function of the radius of the ball that we're compressing the Sun into. So we're starting there. The Sun has a radius of about 700,000 kilometers, and we've just seen that the escape velocity is 600 kilometers per second. So that's where the yellow dot starts. But what if we were to compress all of the mass of the Sun into a smaller volume? Well, the escape velocity would go up. And if we make it smaller still, it would go up further. Smaller still, it goes up further. And we can continue all the way to the point where, hypothetically, if we could get all the mass of the Sun into a sphere about the size of radius 3 kilometers, at that point the escape velocity would reach the speed of light. We would have an escape velocity of 300,000 kilometers per second. So if we can get the Sun into something smaller than 3 kilometers, the escape velocity is so high, it is higher than anything can actually go. No matter, no light can go faster by definition than 300,000 kilometers per second. Therefore, we would have created a black hole. For the Sun, that particular radius, which is called the Schwarzschild radius, is 3 kilometers. And we talk about an event horizon. It's an imaginary sphere. There's nothing physical about it. It's just a boundary, a horizon, where objects can fall into the black hole, but nothing can come out. So for the mass of the Sun, we would need to compress it down to 3 kilometers to make a black hole. But what about other masses? Well, if we started with the mass of the Earth, we would have to take the mass of the Earth and compress it to a volume about the size of a marble, a radius of a few centimeters, in order to generate a black hole with an escape velocity equal or greater than the speed of light. If we were to take the mass of the Moon, we would have to compress that down to a volume smaller than a grain of sand in order to make a black hole. And if we took an even smaller mass, such as, for instance, let's just at random pick the mass of Mount Everest, we would have to compress that mass down to the volume of 1 atom in order to make a black hole. So of course there's no way that we know how to do that for anything other than a star, but just because we don't know how to do it doesn't mean it's impossible. So what did our friend Einstein have to say about gravity and black holes? Well, Newton thought of gravity as a force between two massive objects, so that if we think about mass 1 and mass 2, we can think about a force between them. But Einstein thought about gravity in a different way. He considered a mass as distorting or curving or warping space itself. And we can't really imagine that. We can't imagine a three-dimensional space being curved, because our imagination just doesn't let us do that. So the best analogy that we can come up with is to say, well, what if space were two-dimensional? What would a massive object do to a two-dimensional space? And the answer is, it would make that two-dimensional space warp or curve. And a black hole is so extreme, the gravity is so strong, the density is so high, that it produces infinitely distorted or infinitely warped space. And so we get this traditional picture of a sort of a funnel, if you like, down which matter can get sucked into the black hole. That's not, strictly speaking, an accurate picture, but that's the one that tends to always crop up, whether it be in science fiction or simply any science popularity where we're trying to just understand what a black hole looks like. But if Einstein says that black holes curve or warp space and they produce an infinite curve or an infinite warp, why on earth should we believe something so crazy? Doesn't that sound like a completely ridiculous idea? Why should we believe Einstein just because he says that's the way it is? Well, one of the reasons we believe Einstein is because his theory of general relativity has made other predictions which have turned out to be true. For instance, the orbit of Mercury is almost an ellipse, but the ellipse doesn't quite go over itself time and time again. The ellipse slowly changes its orientation over many, many years. And Newton wasn't able to explain the way the precession of the orbit of Mercury swings around like this. But Einstein's theory of general relativity was able to explain the orbit of Mercury. Not only that, but Einstein made another prediction that if mass distorts space in the way he indicated, then what we should see is that if starlight grazes the surface of the sun, then the starlight won't travel in a straight line, it'll travel in a slight curve. And this was tested in 1919 when there was an eclipse of the sun, which allowed us to see stars fairly close to the limb of the sun, obviously much further away, but in roughly the same line of sight. It was taken during an eclipse because, of course, when the sun is not in eclipse, the sun simply drowns out all the fainter stars in the background. But during an eclipse, some of those faint stars could be seen, and by plotting their positions, it was realized their positions are slightly off what you would expect, unless you take into account that the starlight has been curved because the sun has distorted the space around it, and the light curves because of curved space or warped space. So we believe Einstein. But we can still ask, well, how do black holes come to be? We know that in principle, if we get enough mass in a small enough volume, we can make one. Last week I talked about massive stars that come to the end of their lives. When the fuel runs out, gravity can compress the core of the star. And if the star is massive enough, the gravitational pull on that core can compress it into a very small object, perhaps only kilometers in size. The rest of the star, because of a sort of rebound, if you like, of all the incoming matter, rebounds off the core, and that is the supernova explosion that blows away the rest of the star. But the core gets compressed, and if it gets compressed enough, we can take solar mass objects like 1 or 2 or 3 or many solar masses, and it's possible to compress them into only a few kilometers and create black holes. What happens when matter gets too close to a black hole? Well, it can become stretched and distorted and completely ripped apart, and then the matter tries to get into the black hole, or if you like, the black hole gravity is trying to suck the matter in. But just like water, if you let water out of a bathtub, it doesn't all go down the plug hole at the same time. It's the same for mass trying to get into the black hole. A lot of it ends up circling around the black hole into what we call an accretion disk. This disk can get very hot, and the matter there can start radiating electromagnetic waves. Perhaps visible light, perhaps infrared, perhaps X-rays. A lot of radiation comes out from the region around the black hole. Notice that it also can produce jets of material coming out of the north and south poles. Those jets are still a little bit of a mystery. But accretion disks can form simply because matter, whether it be gas or whether it be a passing star, can get ripped apart by the tidal forces. Strictly speaking, it's not actually the force of gravity, it's the tidal force. In other words, it's not simply that gravity is strong, it's the fact that if a star gets too close to a black hole, the gravity on one side of the star can be significantly larger than the gravity on the other side of the star, and hence the star gets pulled apart. This is sometimes called spaghettification. Yes, that is a real word. And it's also called the noodle effect, to show that whenever matter gets close to a black hole, it can be ripped apart and then mixed up into this accretion disk. As I've said, if the accretion disk is hot enough, it can actually glow in visible light or other electromagnetic wavelengths. So if we saw such a thing, we wouldn't be looking at stuff coming out of the black hole itself, we'd be looking at light generated in the vicinity of a black hole, but it would be an indication that the black hole was at the core. But that's not the only way we can detect black holes. Another prediction of Einstein is that not only does a mass distort space, but if we have a couple of very massive objects like black holes orbiting around each other, or orbiting and then perhaps colliding with each other, it's predicted that they will produce ripples in space, so-called gravitational waves. And it might be possible to detect gravitational waves. So a few years ago, these observatories were set up, one in Washington State, one in Louisiana. Since then, many other observatories of a similar ilk have been built around the world. These very large L-shaped observatories are indicated here, where we have a central building where there's a very powerful laser, which is split into two, and then the laser beams are sent down these very long arms, about 4 kilometers in length. The lasers bounce off mirrors at the end of these two arms and then come back to the central building. What we're looking for is, assuming that gravitational waves are making space ripple, if you like, what we're expecting to see is the length of one arm will get ever so slightly longer and the other arm will get ever so slightly shorter. And then backwards and forwards and backwards and forwards, the length of the two arms will change if a gravitational wave moves through the Earth. So if we fire two laser beams down these two arms and bounce them off mirrors at the end, then when the two lasers come back to the central building, they'll be slightly out of phase with each other because they've travelled slightly different distances. I say slightly with an exaggeration there because the effect that we are expecting is absolutely tiny. If we think about black holes colliding with each other millions or perhaps even billions of light years away, the effect that we're likely to see on Earth is going to be something of order 1 part in 10 to the 20. The changes of length that we're expecting to see because space is expanding or contracting, that's of order 1 part in 10 to the 20. And just to give you an idea of just how small that is, if you're not used to thinking about large or small numbers, if you wanted to measure a distance to a precision of 1 part in 10 to the 20, it's like measuring the distance from the Earth to Alpha Centauri, 4 light years away, to a precision of less than a millimeter. That's the sort of precision that's required to do these experiments. The mirrors at the end of these long 4 kilometer long arms, this is what the mirrors look like, very large masses that are suspended in such a way to try and isolate them from any movements of the ground around them. We don't want an earth tremor, we don't want a train going by, we don't want somebody slamming a door to produce a vibration which makes the mirror move, because we're trying to measure effectively the distance from the central station to the mirrors to an accuracy of parts in 10 to the power 20. So it's a phenomenally difficult experiment to do, but amazingly enough, it is actually possible. The two light beams, when they return to the central station, are put into this device called an interferometer, which is a very sensitive way of measuring very tiny differences in the lengths of those two arms, because light takes a slightly different time to go down the two arms and return to the central station again. But in 2016, it was announced that they had indeed measured the changes, the ripples in space, because of the passage of gravitational waves produced by a couple of black holes colliding with each other in a galaxy more than 1 billion light years away. That produced ripples in space which were measured in 2015 and reported in 2016 when they'd done all of the analysis. At the bottom of that image you see a trace there that indicates how the lengths of these two arms have changed. The red and the blue are the two observatories, one in Washington, one in Louisiana. If you see a trace like that and you say that's the result of gravitational waves, nobody would believe you if you only reported one result from one observatory. But the fact that we get essentially the same trace, a little bit of noise, but essentially the same trace, detected at the same instant in two observatories thousands of miles apart, that tells us that we're not seeing anything local. We're not seeing an earth tremor. We're not seeing a door slam. We're seeing the result of black holes merging 1 billion light years away. So that was scientifically an absolutely incredible result. And of course, kudos must go to the technicians and the engineers who managed to build a laser interferometer with the sort of sensitivity required to measure these tiny ripples in space. A few years later, perhaps you heard of the Event Horizon Telescope. Strictly speaking, not a telescope, but a collection of lots of telescopes around the world, lots of radio telescopes that were all used at the same time to observe the supermassive black hole at the centre of a galaxy called M87. And the supermassive black hole at the core is referred to as M87 star. So this is a radio observation, so don't worry about the fact that it's been coloured orange, that's just for aesthetic purposes. What we're looking at is the glow from the accretion disk which has formed around this supermassive black hole. The accretion disk is hot enough to radiate radio waves amongst other electromagnetic waves. So gravitational observatories tell us that black holes of a certain size have merged together, confirming the idea that black holes are formed by the end of stars' lives. But in addition, we've got evidence that supermassive black holes exist at the centres of galaxies. We believe one like this exists at the centre of our Milky Way galaxy. We haven't got the observations of that yet. So if we know black holes exist, some of them relatively small, some of them absolute monsters, is it possible that black holes are the answer to the question of what is the dark matter that appears to be pervading the universe? If we think about the composition of matter, it turns out that if we subdivide all matter into stuff we know about and stuff we don't, it's rather embarrassing to admit that all the stuff we know about is only about 1/6 of everything that's out there. That 16%, if we subdivide the 16%, it turns out to be mainly hydrogen and helium, most of which was made in the Big Bang. Yes, stars are doing their best to fuse hydrogen into helium. That's what our sun is doing as we speak. But still, most of the matter in the universe appears to be that hydrogen and helium. And 2% of the 16% that we know about is actually stars. So when you look out into the universe and you see billions of stars, each of which might occupy I don't know how many billions of galaxies, it's sobering to realise that all of the stars only account for only 2% of all the matter. And if we return to the left-hand part, we say, well, 16% we know about, but then we have to ask the question, well, what is this other 84%, so-called dark matter? It might actually be better to call it invisible matter, but the name has stuck. We call this stuff dark matter. So if we can only see the 16%, the gas, the dust, the stars, all of the galaxies, then why do we think this 84% is lurking there if we can't see it? What's the evidence? Well, it's just like the wind. We can't see the wind, but we can see the effect it has on leaves on the trees. And it's the same with dark matter. This is the first piece of evidence. If we look at galaxies rotating, well, we can't watch them rotating, but we can measure the speed at which stars are moving. We might expect stars moving in a galaxy, the stars to be moving quite quickly if they're close to the core of the galaxy, but we would expect stars towards the rim of the galaxy, the outer rim, to be moving quite slowly, because those stars are quite a long way from most of the matter in the galaxy itself. But that's not actually what we observe. What we see in many galaxies is, yes indeed, the stars are moving quite quickly near the core of the galaxy, but the stars towards the outer rim appear to be moving just as fast. In some galaxies, they're actually moving even faster towards the outer part of the galaxy rather than those stars closer to the core. So we expect outer stars to be moving quite slow, but what we actually see is the outer stars moving much faster than we can explain simply from the mass of the galaxy that we can deduce from all of the stars. There must be something else there. For those stars to go that fast, the mass of the galaxy must be significantly greater than we can calculate just by working out how much mass we can see in all of the stars and all of the gas. And that is not just true of our galaxy, it appears to be true of essentially all of the galaxies that we have observed. That's one strand of evidence. A second piece of evidence looks at distant galaxies, and if light from distant galaxies reaches the Earth by happening to pass through a galaxy cluster, this happens from time to time just by happenstance, if the light passes through a galaxy cluster, because that galaxy cluster is very massive, and massive objects distort or curve or warp space, what happens is the light that reaches Earth takes a curved path and gets focused, just like a lens. We call this gravitational lensing. And when we analyse images of distant galaxies that have passed through an intermediate galaxy cluster, we can calculate how much mass must be present in order to distort space in the way that gives us these curved lines of light from the distant galaxy coming to us. And when we calculate how much mass must be there in order to produce these distant images, these images of distant galaxies, we find the amount of mass that must be present is far more than we can account for just by looking at all the stars in all the galaxies that we can see. And again, it's larger not just by a few percent, it's larger by a factor of 2 or a factor of 5 or larger by a factor of 10. Whatever dark matter is, it appears to outweigh everything else that we can actually see. This sort of experiment has been done on a lot of images, such as images from the Hubble Space Telescope. Here we can see one in which the foreground galaxy, the orangey galaxy you can see towards the centre, has distorted a more distant galaxy, which is a more bluey galaxy. That bluey galaxy is probably a perfectly normal shape, but it appears to have been distorted into something close to a full circle by the mass of that intervening galaxy. And a rather nice analogy of how we can get that sort of result is to think about a distant object such as a candle and how that gets distorted if the light passes through a lens such as, for instance, the base of a wine glass. The base of a wine glass is a very crude lens, and we can see how the distant candle, in the top right it looks like it's been multiply imaged. We seem to have 3 candles there. In the bottom right we seem to have a couple of candles, and if you look on the bottom left, by adjusting the position of the lens we can actually get that distant candle to look like an entire circle, just like we saw in the Hubble Space Telescope image just previously. So we have evidence that dark matter is there because of the rotation of galaxies, because of the way gravitational lensing works. We have evidence that there's far more mass than we can account for. But what is responsible for all of this extra matter? There are 2 candidates, rather amusingly called WIMPs and machos. WIMPs are particles that we haven't detected yet. That sounds like a bit of a cop-out, but we know that we are made of electrons and neutrons and protons in all of the atoms and molecules in our body. We know the neutrons and protons are made of quarks. And we've got a pretty good idea of how all of those particles work. But maybe this dark matter is made of something completely different, something that we haven't found yet. Despite using particle accelerators for the last 100 years, maybe we've missed the fact that the universe is made of something other than what we are made of. Maybe we just have to look a little more carefully and do a few more experiments to try and find what this dark matter particle might be. But they go under the generic description of WIMPs, weakly interacting massive particles. We don't have to worry about why they're called that. But the other possibility is maybe all of this dark matter isn't a new particle that we haven't found yet. Maybe all of this dark matter is actually objects in the halos of galaxy. A halo is a large sphere that envelops the galaxy, much larger than the visible disk, for instance, of the Milky Way or other galaxies that we see. So maybe there are lots of objects scattered throughout the galaxy that are responsible for this extra mass. And maybe we can't see this extra mass just because it's dark and doesn't emit light. Is it possible that dark matter is actually just lots of black holes? Well, there would have to be an awful lot of them. We'd have a little bit of difficulty explaining where they all came from, because remember, all the dark matter outweighs all of the visible matter by a considerable amount. So there would have to be lots of them, but could we actually detect them if they did exist? Well, that was considered a possibility, and one of the ways of detecting these black holes, even though they're emitting no light, is to start doing this sort of experiment. Let's imagine that we're looking at a distant star, and let's imagine if there are enough black holes out there, sooner or later a black hole might drift into our line of sight for that distant star, and the middle panel shows what would happen. If a black hole happens to line up with a star, then the starlight can get lensed because the black hole will distort the space around it, and that lensing of the starlight could give rise to the star becoming temporarily just a little bit brighter. And then if the black hole happens to drift away, the star will go back to its original brightness. So if we see a star brighten and then fade again in a characteristic way, that could be the sign that a black hole has just drifted across our line of sight. But even if there are lots of black holes, we can't expect this to happen very often, so we would have to look at millions of stars and watch their brightness over a period of time to see if any of them brighten in this characteristic way. And that experiment was indeed done. If we imagine this to be a view of our Milky Way galaxy as seen from the side, so there's the centre of our galaxy, the galaxy bulge. We are in one of the outer spiral arms, so we would be out here somewhere. The experiment was, let's look at all the stars in these objects, these large and small Magellanic Clouds, satellite galaxies of the Milky Way. If we're viewing them from within the Milky Way and we're looking at all of these stars which lie to the south of the Milky Way, well, there's lots of space between us and the Magellanic Clouds. If that space is full of black holes, which it would have to be if black holes are the explanation of dark matter, then there should be plenty of black holes drifting in front of our line of sight to all of the stars in the Magellanic Clouds. We should expect to see these lensing events. So what was the result of this experiment? Well, black holes were indeed detected, but the number of black holes that were detected are nowhere near enough to explain dark matter. So yes, the halo of our galaxy, and presumably other galaxies, are littered with black holes, the corpses of old stars. But there aren't enough of them to explain dark matter. Maybe we're looking for the wrong type of black hole. Maybe. A lot of people seem to believe the answer is in this new particle, this unknown particle which we haven't yet discovered. But the bottom line is we don't know. The jury is still out as to the nature of dark matter. So it still might be black holes, but the evidence is mounting that it isn't. But we don't have the candidate for a new particle, so at the moment we really don't know. So we know that black holes exist. We know that massive stars coming to the end of their life, that end their lives in supernova, can crush the core down to very small volumes, and we can end up with a black hole of the mass of our sun, or a few times our sun, or possibly a few dozen times the mass of our sun. So we know black holes can exist, and we've seen the gravitational waves from some of those black holes merging with each other. At the other end of the spectrum, we know that supermassive black holes exist at the core of galaxies. Supermassive means very massive at the level of millions, if not billions, of solar masses. So you can see black holes exist on a spectrum that range from a few or a few dozen solar masses all the way up to millions or billions of solar masses. Perhaps there are some black holes in this intermediate range that are much bigger than individual stars, but much smaller than the supermassive black holes that we see at the centres of galaxies. But at the moment, there's very little evidence for any that exist in that mass range. But black holes will continue to be interesting. They are laboratories of extreme physics, the extreme gravity, the extreme density, and the extreme electromagnetic fields that exist around black holes will mean that they are interesting objects to research for, I am sure, many, many decades to come. So thank you for listening to Black Holes in Half an Hour.